Yeah, so from standards to practice, implementing effective QoS control in NVMe SSDs. We really started out, when I submitted this abstract, I had a high optimism for standards completion rate, getting well ahead of where it was. So I would still say that this TP is still in early development stages. So we're not going to go so much about where the standards is going to end up, because I don't know. But I get to talk about my viewpoint a lot more. And for me, that's more fun, because I get to say whatever I want and I don't get in trouble so much. To me, when I look at QoS, there's two useful QoS modes that I think are commonly needed in the storage ecosystem. One of those that I hear most discussed primarily is a rate limit mode control. And for rate limit, you're kind of looking at maybe a total, a write, trim, and you're looking at an IOPS and bandwidth type limitation. Or maybe, I chose total, but you could also have a read, write, trim listing there. And I think that they can be equally useful as a set of communicators. But you really want to hit a maximum and then limit somebody. Maybe for one SSD, you might have several sharing it, and they're getting a pretend behavior as though they all have a smaller, less capable SSD, for example. And then when you look at this rate limit mode, I think that there are complexities. I'll get more into this later. But when we look at writes, there's just an example where you have that read to write scale factor, and what happens when you have write amplification. And I think that inside of an SSD brings around some design considerations on how do you manage to deliver a good QoS to the host. Secondary mode that I think I'll get into a little bit lighter, but I think is also valuable, is a priority mode. Kind of focused on reducing head of line blocking, or perhaps maybe the other way that I think about it in my mind is you have some very high-paying end user, and you want that high-paying end user to get their money's worth, so they get accelerated access to their data and their storage. Within a rate limiting mode, we can look at that, and we might, inside of the SSD, be able to implement a token bucket in order to move commands forward through the system. Token buckets, pretty common, and they're kind of an inverse of a leaky bucket. You can reframe the two, one as the other. But for a token bucket, you add tokens into some bucket, and if you have some maximum, you cap and you lose any excess tokens, so you don't continue to accumulate. And anytime you have an arriving command, that command will consume some amount of tokens and proceed onwards past this checkpoint. Because we're storage, we don't have some of the luxury that networking has, right? Networking, you can drop packets, and that'll happen often when they have congestion, other kinds of things like that. With SSDs, we don't want to change the assumption. You send a command into the SSD, it's going to send a completion back. Worst case scenario, it'll be an error, but it's going to progress through that SSD. And so SSDs, in networking terminology, I've found this to be called traffic policing, where you're never going to lose a command, and you'll queue up those commands. And we have them stacked up here, 2, 3, 4 commands there. And we won't lose them, but perhaps possibly we would progress portions of commands forward at a time. But eventually, those commands should all complete, even if it's only incrementally progressing through each command. With rate limit mode, 2 example use cases that we might possibly set up, and these are a little bit kind of set up in my mind when I am designing an SSD. I want to talk about what are the test cases, right? And these are 2 simplistic test cases that I think describe some desired behavior of an SSD. So 2 different tenants, VM1 and 2 shown here, and I'm going to have VM2 idle. And VM1, I want to provide 75% of the drive performance. That might be one example test case. A second example is maybe I have the other VM2 active, and I've provided both of them 75% of the drive performance, well, we still need to know how that's going to perform, right? We want that to be graceful still. So in this example, where the drive is overprescribed, we probably want the SSD to be shared 50%. We don't want the one VM to get 75% and the other to be choked down to 25%. We want a graceful overprescription behavior, and I think is a requirement of an SSD. For priority mode, we might set up, again, I'm calling them VM1 and 2 just so I don't have to change the drawing. And VM1 might be high priority for short bursts of time, for example. VM2 might be more constant activity. And this could come up in several use cases. I already talked about a high-paying AI customer coming in with some latency assurances. But the other is that maybe VM1 is maybe a file system. And so I'm calling it VM2 still, but that might be the file system traffic, whereas VM1 might be an end user where their reads and writes need to get accelerated access to the SSD. With one potential goal in these setups is that VM1 latency difference would ideally be minimized when you compare it when there's an idle compared to an active VM2. That would be one test to make sure that that urgent requirement from VM1 is actually being met. I think that something's come up in a lot of conversations I've been involved in. We have in NVMe already standardized round robin, weighted round robin, submission queue fetching, and how does that make sense with QoS? And to me, of course, we have more development to go, but to me, it looks like they can be very orthogonal developments. I have drawn here, what I'm seeing is we're really talking about a controller rate limiting, right? And so what we're concerned with is we have the top controller and the bottom controller each having a different rate limiting. And that rate limiting is shown on the back side of which controller is moving at which time, which one's allowed to progress forward in their commands and their traffic. And that decision can be made orthogonal and above which controller is active. When you're within one of the controllers, I have shown here weighted round robin versus round robin. It gets to make an isolated decision internal to itself and say, oh, well, which submission queue needs fetched? How am I going to work with my time, my commands? Which ones are moving forward? And so it's kind of an independent and an orthogonal decision in my view of how this can be implemented. And so I don't think that we need to impact existing NVMe standards. We're going to be able to intermingle and play well as my feelings on how that should develop there. That being said, I've shown the ability of one controller to set weighted round robin or round robin. I think it's reasonable that weighted round robin and how that intermingles with your rate limit or priority settings might be a little confusing. So standing where I'm at and looking into the future, I'm thinking that it's going to be more robust to set up round robin inside the controllers. You'll likely be able to have more testable behaviors. And the weighted round robin, that intermingling, what expectation of QoS is a little bit more question mark. Going to end up being more system specific, test condition specific, I think. When I look at implementing quality of service in real SSDs, we want to, there's a reason that architects have a job, right? It's not easy to design an SSD to begin with, and now you're going to talk about sharing all those resources, trying to prioritize all those resources in a different manner, perhaps waiting or allowing different traffic through. And something that I like to point out is that you might, in one SSD, you might have NAND-gated behavior in fully read workloads. And likewise, when you're in a full write workload, you also might be NAND-gated. But frequently, when you're in a mixed workload, you'll find that your DRAM bottleneck, or maybe NAND channel bottleneck. You'll find that you're hitting different bottlenecks at different capacity points, at different read and write ratios, and those dynamic positions of where you're hitting a bottleneck are real design problems. So I think that while real SSDs are hard, I think that what we need to do in a standardizing setting, we need to do the best effort of simplifying that and making it a simpler handle and something that's more manageable to understand. It might not be perfect across all test conditions, but I think that with bounded transients and things like that, I think that it still should be very useful for the ecosystem to use. So in my mind, there's a potential idealized goal of communicating a media access target, even though I'm already acknowledging that's not the real world situation, that it's not really truly achievable. When I look at reasonable QoS for write scaling choices, I start off and I look at a total being composed of read, write, and deallocates. When we just look at the writes, for example, we can scale a program time to read time when you ratio that at a per bit basis, so time on the NAND. So every NAND, every SSD vendor, every generation is going to be a little bit different, but I think it makes sense that you can quantify a write scaler here that would be proportional to your program time and read time per bit. That only works with sequential writes. SSDs do garbage collection, right? So we need to further complicate this when we look at non-sequential writes. So now we have, what do we do with this WAF scaler, the write amplification? I think there's a couple of options, and I don't know what's going to end up being normal, but I can see one is potentially there's some WAF scalars that's determined by the drive, like maybe a worst case. Another could be a representative value that is some nominal write traffic that's characterized, maybe by the customer you're delivering this drive to. I think that there's another possibility I would like to see enabled is the WAF scaler being proportional to actually experienced WAF. I think that this might be, it might be requiring some connection to the FTP RUHs, but that is something that I believe is achievable in SSDs. And of course, there's other solutions, right? I'm putting out a few conversation starters and not setting a prediction on what's going to actually be happening there. I think that as we move into other complexities, I think deallocates are number one complexity in my mind. We look at that and we see that most deallocates are DRAM or CPU-bound operations. And their interactions with reads and writes can be very complex. What's the length of the ranges that you're using for deallocates? How many are you sending at the same time? That kind of thing. Are you implementing these trims in a foreground or a background implementation? Very nonlinear interactions, I think. And so I'm looking at this already and I'm saying, let's take this and have a reframed goal, and it's more like we need to limit deallocates and in a proportional manner on how much they're impacting reads and writes. And really, since we're talking about the impact on reads and writes, I'm also kind of leading us to test cases with our customers that are, here's a moderate amount of trims, and let's make sure that it doesn't blow up and halt the movement of reads and writes. So I'm leading towards a focused 90% reads workload and a small amount of trims kind of thing. Transient workloads, I've already touched on that a little bit. Transient workloads can have different bottlenecks when they have different ratios. What about when they transition between their ratios of reads to writes? For SSD implementations, I think that we need to make sure that we monitor those transitions and make sure that they're bounded transitions, right? We need to monitor them through our QA and development, but it's hard at this point to say that let's design for those transitions. That's a huge problem that I don't know the industry has a common viewpoint on. Okay, design to what goal? And of course, we have writes that are misaligned to the indirection unit, causing a modify write. These are small writes, or maybe their head and tail is offset from the IU. We'll see those increasing commonly in QLC SSDs, large capacity SSDs. So how do we tolerate and resolve those? I'm expecting discussions on these in NVMe, and I'm looking forward to those. Feel free to join them if you have an opinion on where they land. So for a standardized QoS parameters, I believe that we need to have a common set of parameters that are going to work across all SSDs, vendors, generations, clients or enterprise, different capacity points, and others. I think that to try and do a perfect set of parameters for enterprise would be nearsighted and wouldn't enable the client market, for example. I think that the parameters that we arrive at need to be simple enough that a poorly informed host won't get themselves into too much trouble. I think that if we go too complex, it very much can end up otherwise. From a customer action, we're kind of, I set up this slide in saying that we're not having perfection on parameters. So I think that there's high value in a small number of representative subset of target workloads. Where do you care about this? What is actually a target useful workload? And make them small so that we can focus time and really dial those in as SSD vendors. Because of the latency on urgent and things like that, I think that the importance of a enclosure and CPU settings and other things like that are very important, right? We see that already in performance benchmarks. Are you connected on the local NUMA? Are you set on hyperthreading on or off and things like that? Having that commonly between the vendor and the customer is highly important on when you're looking at the latency. When we look at similar with what we already see in customer quals, there's already performance acceptability ranges. I think that we're going to have to see that QoS performance requirements. Again, the bounds of acceptability targets will start with one generation, and next generation we can incrementally improve. From a vendor actions, we need to design for the provided workloads. I think that there's a very high sensitivity to the variations in settings and workloads. And I've already highlighted before the fact that we remain bounded in our behavior when there's transitions, because the customer is only going to provide us target workloads. But what happens when we transition between them, if they burst or if they are varying from that, right? Software continues to develop, but the drive we shipped stays the same. So when that software develops and it's now out of that perfect characterization, how do we behave? So when we continue and we look at the earlier examples in a customer qual, we might take that idle VM2 and we might look at it as for acceptability in a customer qual type situation where we're measuring 100% of the drive performance. We enable the QoS settings. We measure and we check that we're within the 75% was the design target. Are we within those bounds of acceptability? Similarly, when we're overprescribed, we would enable the QoS settings and measure the performance and look for within boundaries of 50%. Are we sharing the drive well? Is that stable and smooth? Is it 50% on average only if you go for a 10-minute average? If you go for a 10-second average, it's all over the place. with QoS and the priority mode, we might look at the 2 example workloads. One might be VM1 would have QD4 random reads, and VM2 might have QDepth 128 and a mixed workload. We might look at that VM1 3 nines latency, and we want to see a degradation of no more than 50%, for example. Another example might be VM1 submitting 128 random reads on the second every second, but not maintaining a queue depth of 128, just a burst of 128. VM2 might constantly have a high queue depth of sequential writes. And again, we might set something where we look at the 5 nines latency staying below 10 milliseconds so that we can have those reads that burst in 128 at a time, that they're happening with good latency and very few outliers. You can hear it by the way I spoke through these, but I think the examining things in nines is high value. From a design engineer, I see these and I'm able to propagate nines targets into different component targets for an SSD. And so there's high value in receiving those requirements from a customer in that manner. This is in contrast to what I've seen historically. There's been a lot of variations over time. And these, as we move from generation of PCIe generation to PCIe generation, they need to be re-examined. What is the measurement time that's shown in blue, curly braces there, that you're examining over? What width of peak? Shown here, I have a pass because there's a narrow peak that's acceptable, and there's a fail because there's a wide peak of variation. These seem to be re-examined every generation, or if you don't re-examine them, they inherently become tighter. And that's not always needed or intended. Actually, the pass with a very narrow peak is looser. So to me, when I look at the latency in nines, it's more robust generation to generation. And I meant to pop this up earlier, and one thing to note, of course, is if you ever have a quantification where the performance measurements are over time, there can be a one-time translation over to nines, right? It's not as though they are in disagreement. It's just one-time translation. So through the slides here, I've talked about there's development in NVMe. Come join it. Argue with me. I look forward to hearing others arguing with me, giving other opinions. I think overall it's going to be a really impactful change. I think the larger our SSDs get, the more important the sharing of one SSD is. So getting this right and setting something, this is a first stone. We'll continue to develop, so let's make sure it's a good direction to start. The QoS parameters will be simplified, but we can set expectations, and I think we can work together to have some useful target workloads to develop towards. And I think that overall, one thing that'll be difficulty is when you have an SSD that gets outside of its initial usage and someone picks it up off the street and starts working with it, that person might expect the same behaviors to work perfectly in extreme settings. And that's not going to work, right? So there's a little bit of an education, and what can we do to prevent people viewing that as a bug in the system? And they would view it as a system bug, right? They're trying to use a drive that, and they probably are not working with this overall. And then latency, I think, is going to become of extreme importance during customer quals and looking at the performance and behavior of QoS. So that's my presentation, and I welcome any questions.
Are you looking only to set floors or also ceilings? And I'm asking that in the context of managing drive wear over its lifetime. Could you use these mechanisms for that?
So are we setting floors and ceilings? So to me, right now, I think that setting just a ceiling makes sense. If there's a strong use case for floors, I think that we can bring that in, but that hasn't been my focus. This is like a guaranteed access.
Guarantees versus limits.
Guarantees versus limits, yeah. So,
I mean, the QoS is kind of guaranteed, right? Whereas QoS is in the category of guarantee, I think. Whereas if you're allocating the resource distribution, that's more of a limit. You get 30% of the SSD, that type of thing.
Right? I understand why you would want a minimum guaranteed access to the drive. I guess the biggest question in my mind, do we need that in a step 1 QoS delivery, or can that be a second one, right? Can we tier that in? And I'm not sure that I have the answer, right? That maybe we do need to have both come in at the same time in development, or perhaps we can just keep it simple, the first one, and come in later. It's a good question, yeah.
Right, Dan, I would observe that there is some limit functionality in what you presented. For example, in your 75-75 two VM example, each VM is guaranteed 25% even under worst case loading and service of the other one. But that's a very simple example, not to be confused with the general limit framework that you just asked about.
Yep, thanks.
So who makes the QoS request? So I'm trying to figure out, so what I tried to piece together from beforehand is that the QoS setting that we're giving is I want at least this much of the drive. Is that correct?
Yeah.
Okay. Then who sets that?
Let me correct myself. Okay. I have a tenant, and I want to limit that tenant to not exceed some bandwidth or IOPS.
Okay, so a tenant, so is it a privileged controller that sets these limits?
So
another controller?
In NVMe terminology, we've had a lot of things like the migration of migratable controllers and the migration management controller. And NVMe terminology, I'm not
there
specifically
is something
sure.
called a privileged controller. That's like there are privileged actions that are.
The expectation is in a typical SSD, a controller would get the privilege to set these parameters, and all the other controllers don't know that they're being set, and somebody at the host is managing how I'm orchestrating the QoS in the whole SSD.
Yeah.
Now, in NVMe terms, we'll just say somebody's managing it. Who that is or what it is, that's up to the final implementation and who gives out those commands.
Right. In real-world implementations, we expect the primary controller to be the migration management controller, to be the QoS setting controller, right? That's a nominal expectation, is to have those make sense. But NVMe terminology yet to be decided.
So I missed the beginning part, maybe you covered it, but I think you have some amount of PCI and system level things coming together, right? That's not what you probably covered here, and that affects the overall cost that is desired. So maybe you can get to some point where you can rate limit your controllers to achieve some amount of quality of service, but to give some amount of minimum guarantee, you also need other things to play along, right?
So I'm trying to digest the question.
So you're going to split, so you have 2 or more controllers. They're all sharing the PCI lane. They're all interacting with your CPU, root port, memory, everything. So there's a whole bunch of system level dependencies here. So when we are talking guarantees, you need to have the whole platform deliver that system guarantee to you. So where is the assurance coming from?
Yeah, you missed. Let me help you out. Shai, you missed the first part of the talk. This is an SSD QoS talk. You're absolutely correct about QoS at the larger scope, and I'm sure Dan would love to hear from people who are trying to make that happen.
Yes, yes. And actually I did, that's a great question, and actually the portion I did touch on, overall QoS is going to be owned by the system developer.
If you're saying you are splitting your SSD, if you're saying you're splitting your SSD to give
Right.
40% to one controller, 60% to the other controller,
Right.
that's okay. But if you're saying you're guaranteeing, I will split whatever IOPS, right? That's
Right.
different.
The sharing, yes, and that's also in a customer qual situation when we're designing. I think that it's always been important to say what enclosure and connectivity and CPU and so forth have been using. But the importance of that jumps another order of magnitude in importance for how are you examining that QoS, because I believe you're right. You're going to be controlling that QoS at a system level, building blocks, and this is a SSD building block, so you need to set assumptions and be able to use that across vendors, right? So I agree, yes. Thanks.
All right, we're out of time, so let's thank Dan.
Yeah, thank you.